Permutations and combinations. This is self-paced. You should have either received or printed out a copy of notes. This particular lesson is going to be a combination of when to write stuff down in your notes and when to just watch and listen. Sometimes it's important to just watch and listen and then write. So I'll let you know when you should be doing which. But understand that every bit of information on this presentation is not necessarily something you have to write down. First, you should have your notes. Find your notes, and at the top it should say Fundamental Counting Principle with examples. This you're going to be writing. Now, the fundamental counting principle, it says if decision M can be made in M ways, meaning you got some decision, it can be made in 5 ways, and decision N can be made in lowercase n ways, then the two decisions can, when you make them together, when you have to make them both, they can be made in M times n ways. An example, an ice cream shop offers a choice of 3 cone sizes, 15 flavors, and 8 toppings. How many cones are possible if you can only choose 1 flavor and 1 topping? Well, remember that you can pick the first cone, small, and then you've got 8 different or 15 different flavors, and for each flavor you could have 8 different toppings. That means that you have 3 sizes, 15 flavors, 8 toppings, or a total of 360 different cones. That's quite a bit. Okay. The next example, license plates. They consist of 3 letters followed by 4 digits. How many different license plates are possible? Okay, 3 letters. First off, letters are, how many letters are there? 26. How many digits are there? 0 through 9 means there's 10 digits. So what you have to do is you have to tell yourself that you've got 26 times 26 times 26. You getting the idea? And then what do you have to multiply by? 10 times 10 times 10 times 10. Now this is for just one that gets made up. Obviously there are vanity plates and you can have up to 7 characters, and they could be all letters or all digits depending on what you want. So, but the standard one looks like this, and it turns out that you do 26 cubed times 10 to the 4th for a grand total of 175,760,000 different combinations. And that's when you keep them in this order. When you make it so that you could have any letter or any combination of letters and such, remember that would be 36. 36 to the 7th power would just be huge. So we're not going to run out of license plate numbers. Now, erase these guys over here. The next one up, let's look at Nick's science test. It has a section with 12 true or false questions. How many different ways can Nick answer these questions? Well, first, does it matter that it's true or false? Maybe. Think about it. It does. It's true or false, 2 to the 12th. Okay? That means 4,096. Okay? Now, to enter their home, the Clayton family enters a 4-digit code. How many codes are possible? Assuming that it's just the digits, not the star, not the pound. Don't include those in your code. Think about it and let me know. Did you get 10 to the 4th? Good. There are 10 different codes, and each one could be entered. Nice job. Now, let's take a look here. Selecting and rearranging. Permutations. arrangements of objects from first to last where the order in which the objects are selected is most important. You have 5 books. Now this part, by the way, is not on your notes. I want you to set your notes aside and just listen and just understand where the order in which the objects are selected is most important. So you have 5 books you wish to arrange on your bookshelf. How many different arrangements are there for you to choose from? Well, think about this. You have 5 positions from left to right. How many ways can the first space be filled? Well, if you have 5 books, any one of the 5 books could be first, so you have 5 different options. When you move to the second place, though, how many books do you have left? You have 4 books left. If you only have 4 books, then that means there are only 4 different things that can happen in that second position. If you continue this way, then you realize that you have 5, then 4, then 3, then 2, then 1 different possible arrangements. That makes for 120 possible arrangements. Notice we're using the counting principle. There were 5 possibilities in the first place, 4 in the second, 3 in the third, 2 in the fourth, and only 1 possibility for the 5th place. An equivalent mathematical statement is that there are 120 permutations of any 5 objects. Okay? Permutations. Order matters. Now, another one for permutations. Let's take a look here. Arrangements of objects from first to last where the order in which the objects are selected is most important. You own 7 different sweatshirts and want to wear a different one each day of the week. How many different ways can this be done? Well, here's your 7 sweatshirts. How can it be done? And did you get 7 times 6 times 5 times 4 times 3 times 2 times 1? Because remember, there are 7 days in a week. First one, you've got 7 sweatshirts to pick from. After you've worn it, it's dirty, it's in the wash, and you move on. And yes, I know that says Forest Park. That's where I taught when I made this slide. Okay, let's try this one. There are 26 letters in the standard English alphabet. You decide to create a 26-letter word is in quotes, using every letter once. How many different 26-letter words are possible? This number will be large, so be sure to express it in scientific notation. You can pause the video while you do your multiplying. And you're back. Did you get 4.03 times 10 to the 26th? It's a huge number, way huge. And was it not a bit tedious to type in 26 times 25 times 24 times 23 all the way down to times 1? And yes, you could save yourself some hassle and not type in the times 1. I get that. It is tedious. And therefore, mathematicians came up with something that we call factorials. You're back to your notes now. In the middle of your page, you should write this information down. The product of all natural numbers from n to 1 is going down. Okay, that's what a factorial is. So 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that's 362,800. Big number. You can also do 12 factorial. I didn't write it out, but it's 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Boom! There's your answer. 8 factorial. You can also do arithmetic with factorials. 17 factorial divided by 11 factorial. Okay, and there's a number. 0 factorial is 1. Whoa, wait! Where do we get 0 factorial? Well, factorial is how many ways can this number of objects be arranged? So, in our book example on the shelf before, we had 5 books, and we wanted to know how many different ways we could arrange 5 books. Well, if I have 0 books, how many ways can I arrange 0 books on a shelf? Why, only 1 way. That's a special one. Okay, and that's why the little asterisk is there. So, Multiplying so many numbers seems tedious. Is there a better way? Of course there is. Here we have the calculator. The product of any positive integer with all smaller integers to 1 has a special name and notation. It's called factorial. Where can you find it? Well, I've shown you there, and I'm going to bring it up here. Hang on. Let me pause the video and pin my little guide to my screen down here. Hang on. Okay. So now I'm back, and I've got them pinned here. So what you're going to do when you want to do factorial with your calculator, obviously you have to turn it on. Okay. And then you're going to hit math, and then you're going to want to go over to probability. And notice here's your factorial right down here. Okay? But here's the little bit of a tricky thing. If I want 6 factorial, I need to first type in the 6, then go to math. And by the way, you can click right 3 times, you can go backwards once, and go down to factorial, hit it, and hit enter, and it will give you your answer. Okay, so again, that's math, probability, and then number 4 is where you're going. Okay, you can try that and do 12 factorial. You should get 479,1,600. And then 0 factorial in your calculator should also give you 1. Because the 1 is the number of ways in which 0 things can be arranged. Now, if you're taking the SOL, there's 1 year, this 2019 is the last year where you can actually use the TI calculator. After that, you're going to have to use Desmos. How do you use Desmos to do factorial? It's not hard. Here's Desmos. And for factorials, it's really easy. If I want 5 factorial, I simply type the number 5, and then I type an exclamation point, and notice right here, it gives me my answer. I can come back here and I can type in 12 factorial. I can back up and say 26 factorial, and there's my number. Okay, so it's very easy. There is a factorial function. If you click on functions over here and you go to stats, notice you've got your factorial. All it does is it gives you an exclamation point. Well, you can just hit the shift key and type in the exclamation point. So not a big deal. Okay? Moving on. Permutations. Again, you are on your notes. So what you want to do maybe is take a second. Make sure you've got your notes there. Write in permutations, an arrangement or lineup of objects in which order matters. Now, here's the permutation formula. N factorial over n minus r factorial. Now, this is a little bit different. What we did before, when we just did plain old factorial, that was when we wanted to know how many ways a given number of objects could be arranged. Now what we're going to say is, I have more objects. I'm not going to use them all. In other words, we have 26 letters in our alphabet. We don't have 26-letter words all the time. Sometimes they're only 5 or 7 or 8 letters long. How many 5-letter words can we make out of our 26 letters? Order matters. Permutation. Okay? So, here, n is the total number of objects available. R is the number that we're going to use in our arrangement. Now, do you have to memorize this crazy formula? No, you don't. First, it will be given to you on your formula sheet for the SOL. Second, I don't know anybody who's ever had to use it because the calculator does permutations, and so does Desmos. But an important shortcut to remember is if you're going to use all the objects to arrange, then it's just n factorial. Now, I'm going to look at 2 examples. The first one, how many ways can you arrange the letters in the word dinosaur? Okay, so you've got 8 letters, and you're going to arrange them in 8 different ways, or you're going to use all 8 letters. Notice that there's no letter in the word dinosaur repeats. So it's just 8 factorial. Now, if I have 7 students who are competing in a geography bee, how many ways can they finish in first, second, and third place? Order matters. Bobby could get first, or Bobby could get second, or Bobby could get third. So if I have 3 kids, I could have lots of different ways that they could finish first, second, and third, right? So you've got a total of 7 children or 7 students, and you've got 3 places. So it's 7 factorial divided by what is essentially 4 factorial. Notice here that you can cancel all of these guys, so it's just 7 times 6 times 5. And that turns out to be 210. Now, while this is convenient in a way to simplify things, we're going to look at some ways to do it on the calculator in just a minute. But pause with your note-taking now. You did your examples down to the bottom of the page. What I want to do is I want to talk about some other examples just to give you some more things to think about. So a 26-letter word using every letter of the alphabet is not realistic, nor would words that long be useful. Often we want to use only some of the objects in a set to create a variety of arrangements. That makes more sense. So, suppose 5 different letters are used to make a word. In this case, a word does not have to be one found in the dictionary, simply 5 different letters. How many words can be made? Well, just like the bookshelf, imagine 5 spaces to hold each of the 5 letters. Now, however, there are 26 choices for the first letter, 25 choices for the second letter, 24 for the third, and so on. This results in the following: 26, 25, 24, 23, 22, all multiplied together. That many different words. Notice, since there are only 5 letters used, this is not a full factorial. It's called a permutation. There are 7,893,600 permutations of 26 objects taken 5 at a time. Okay, notice the first place I used 26. That one letter can't be used again, so I've only got 25 in the second place. Now that letter can't be used, and I'm down to 24 letters for the third place, and so on. Again, here's the permutation formula. Here's what it looks like, what we just did. The formula is given on the formula sheet, so don't worry about memorizing it. It's just a way of understanding what you're doing. Now, there is an easier way, using the calculator. And again, you do have to type in the number first, then go and pull up the function, and then type in the number. So, let's try this with the calculator. Again, we turn it on. I'm going to get out of this just so you can go through everything. Hit clear. We hit math. We're still doing probability and/or statistics. And notice here's NPR and NCR. We're going to look at NCR later. NPR is permutations. Now remember that I said we have to put our number in first. So what we have to do is we have to tell it how many items we have total. So in our word example, we had 26 letters. And I press math, I go to probability, and I come down here to NPR. So I had 26 letters, but I only want a word that's 5 letters long. How many different words? There's my 7,893,600. Okay. If we wanted to compute 6 permutations, how many permutations are there of 6 objects taken 3 at a time? We would type in 6, math, probability, come down here to the NPR, press enter, and press 3. Press enter, and we would have 120. Now, can we use Desmos? Of course you can. With Desmos, you're going to come over here to functions. Now, Desmos is a little bit nicer. And up here, notice we have trig functions, stat functions, distribution functions, miscellaneous functions. We're just going to stick with the stats right now. stats, and notice down here is our NPR. I press this. It gives me NPR, but this is a little bit nicer because now I can tell it I want 26 objects taken 5 at a time, and it gives me my answer. If I wanted the 6 objects taken 3 at a time. So I can just keep, once I have NPR up there, I can just keep going back and playing with it. So again, to get to that, you click the Functions key, and you click on Stats, if it's not already there. And then the bottom row is what we're looking at. Okay? All right, good job. Now, almost done with this section. First, before we look at the rest of what we're doing, I want you to look at the bottom of the, at the top of the page there, you have 7 through 9, and there are 3 problems that are with just permutations. Pause the video and try those now. Great. All right, check these out and see if you got them right. Oops, maybe. There we go. Did you do good? 4 classes. How many ways can these 4 classes be arranged? 4 out of 4. On the other hand, 16 players in the baseball team, 9 batting orders, a lot of different ways. Because you only have 9 players at a time. And then the representatives. Okay? Now, moving forward, there are 2 more problems there. And I'm just going to show you what the answers are. This is not on the SOL, but it's good to know, and it's not difficult. If you wind up taking AP Stats or Stats, you might run into this. How many different 10-letter arrangements are possible using the letters in the word automobile? And how many different 9-letter arrangements are possible using the letters in the word disappear? Okay, first off, you got to look at, in both of these words, there are letters that appear multiple times. So in automobile, I can't tell the difference between one O and another O. So therefore, I take the 10 factorial, my 10 different arrangements, and I have to divide it by the 2 factorial because it doesn't matter which O I used. Same thing with number 11, right? A appears twice, P appears twice. So 9 factorial gets divided by 2 factorial times 2 factorial. Again, it's because you can't tell the difference between one P and another. Ha ha. All right. Now, moving on. Put your paper down for a moment and just listen. The governor is visiting your school and you need to assign seating for 14 students. Unfortunately, there are only 6 seats in the front row. How many different ways can you select and arrange the 6 lucky students? First, how many students are you selecting from? Okay, well, that's easy. 14. How many students are you selecting for the front row? 6. Well, if order matters, let's say whoever sits at one end is actually closest to the governor, well then, order matters, and I can do a permutation. And I get 2,162,160 different arrangements. Let's think about it. The governor is probably sitting up on stage, and nobody in the front row is any closer than anybody else in the front row. They have an unobstructed view. So, in this case, we have what we call a combination. Sometimes order is not important. In the student seating example, it really isn't important where you sit in the front row as long as you're in the front row. So in this case, we want a combination. Combinations are collections of objects selected from a larger collection where the order of selection is not important. It's like making a salad, okay? It doesn't matter if you put your cranberries and your lettuce and your cucumbers and your radishes and tomatoes in any given order. You're going to toss it all up and it's just a salad, okay? Combinations, order does not matter. So here, go back to your notes now. Combinations, we write it NCR. It's a group of objects in which order doesn't matter. The formula, there's the formula. And realize it's going to be given to you. Now, an important shortcut if you want to know how many combinations of 8 can I make out of 8 objects, it's just one. All 8 objects are there. If you're using every single object and it's just a combination, order doesn't matter. There's only one way to do it. Okay? Now, if we take our student seating example, okay, we want to say for each group of 6 students, how many permutations are there? When order matters, there's 720 different ways to arrange 6 students. It's like 6 factorial. But, so I don't care all the different arrangements. I just want one. So what I'm going to do is I'm going to do a permutation, okay, of 6 students out of 14. But then I'm going to divide by all the different permutations to find out the number of different combinations. Again, this is just another way of looking at what we're talking about when we mean combination over permutation. If you want, pause the video and read through it. Okay? Remember, we divided by all the different arrangements. This is how many ways 6 students out of 14 can be arranged. But since we don't care about the arrangements or the combinate or the order, we can delete each time. Each group of students, 6 students, counts once. First, the combinations formula. Blech. Yikes. Do you have to memorize it? Absolutely not. It will be on your formula sheet. Additionally, you can use your calculator. Here, if you're going to use the calculator, we turn it on. If we want a combination of 2 objects out of 5, then I have to type in 5. I press the math key. I go to probability, and this time I come down to combinations because my order doesn't matter. I press enter, and I press 2, and I press enter. So again, it's math, probability, and there we are. Okay? Number of combinations. And you can try the same thing with 14C6. Desmos, of course Desmos does this. Notice we have our stats. I can get rid of this guy and I can say this time I want a combination. I have 14 total students and I want 6. 3003. The nice thing is I can either click on these numbers here to enter numbers, and here's the comma over here, or I can just use my keyboard. Okay? Oops, let's go back to our notes here. So, I just did combinations using Desmos. You are assigned to create a committee of 4 teachers from the 230 in the school to oversee the senior class. How many different committees of 4 teachers are possible? Does the order matter? It's a committee. No, order doesn't matter. If you're just a committee, you're just a group of people who are going to do stuff together. So, out of 230 people, you want a combination of 4. That's the answer you should get. If unsure, go ahead and try it on your calculator. Make sure you know how to do it, or try it on Desmos. Either one. Now, oftentimes the most difficult part of a problem is the determination of whether the order matters for the items selected. We're going to look at that in a minute. But before we do that, go back to your notes and try problems 12 through 16 on your notes. Pause the video and try those. Okay, you're back. How did you do? Bueno, bueno, bueno? Hopefully you did well. Now, realize that you in no way, shape, or form have to put down the formula. I have the formula there just so that you know what it is, but you don't need it. As long as you know that it's a combination, not a permutation, combination, the order does not matter, and you can use the calculator. Okay? Now, in each of the following situations, we're going to look and decide if we're being asked to find the permutation or the combination, and then perform the correct calculation. So, we need to select the starting 5 players from a team of 12. Now, I know I've got a little basketball there. Ignore the basketball. Pretend it's like 5 kids are going to go out and play tag. Okay? I did not say there are any particular positions. So we need 5 players from a team of 12. Does order matter? No. Order doesn't matter. Okay? All starters are on the court at the same time. I mean, again, If I told you that they had particular positions, that would be different. Now, here I'm going to distribute 9 different books among 15 children, given no child gets more than 1 book. Okay? 9 different books. Now, if you've already read a book, do you want that same book back? No. Does order matter? Yes, because I could get one of each of the 9 different books. And each time it would be a new thing for me, or a new thing for that child. So the order does matter. If it was the same book, order would not matter. Different book, order matters. So I have 15 children who will get 9 books. There are 1,816,214,400 different ways to do this. Now, how many ways are there to pick a subset of 4 different letters from the 26-letter alphabet? Subset. This is where you just have to have the vocabulary. A subset is just a group. It's not in any particular order. So therefore, since order does not matter, this is just a combination. How many ways can the 3 offices of chairman, vice chairman, and secretary be filled from a club with 25 members? Okay, first, you got 3 offices. Are the offices the same or different? If they're different, then the order matters because whatever somebody has to do in each one of the offices is different. So order matters. Okay? Catching on? So, when you turn to your next page in your notes, you're going to see that it says permutation or combination. Woo. Permutation or combination. Which one is it? Well, you decide. Permutation or combination. We're going to look at the first one. How many ways can 4 candy bars be chosen from a store that sells 30 candy bars? Well, think about it. Is it a permutation or combination? Combination. Okay? I didn't say that they were different. How many ways can 13 students line up for lunch? That's just going to be a factorial. It's a permutation, but it's the same 13 students. How many ways can you make a 3-letter arrangement, order matters, out of the letters in the word trapezoid? Well, first off, do we have any repeats? No. Order matters, so it's going to be a permutation. All right, pause the video and try the rest of these. We did the first 3. You now have 4 through 12 to try. Go ahead and attempt that. Pause the video. You're done? Fabulous. Here you go. How many books can you choose? 2 books from a shelf of 40? Doesn't matter, you're just getting 2. Okay? It doesn't matter which order you pick them in, you still have the 2. You're 1 person getting 2 books. How many ways can 12 swimmers finish first, second, and third place? Permutation. Moving on. How many ways can Mrs. Sullivan choose 2 students from 27 to help out to put calculators away? It doesn't matter who's picked first or who's picked second. You're both putting calculators away. So order does not matter. You have enough tickets to play 6 different games at the amusement park. If there are 14 games, how many ways can you choose 6? Again, order doesn't matter. You're going to play all 6. How many different ways can 9 trumpet players in the marching band line up? That's order matters. And it's just a factorial because you have a total of 9. 7 students work together on a project. How many ways can their teacher choose? 4 to present the project. You got it. Combination. They're all presenting. 18 offensive players on the hockey team. How many ways can the coach choose? A left wing, center, and right wing? Does order matter? Yes, because you're playing a different position. So you've got permutations. Getting easier, I hope. How many different 12-letter arrangements can be made using the letters in the word Indianapolis? Notice what I've done here. Okay. How many do we have extra? I have 3 i's, so there's a 3 factorial in the denominator. We have 2 n's, right, and 2 a's. 2 n's and 2 a's. Whoops. And 2 a's. So that's all in the denominator, and we want 12 different. So it's a permutation, but again, we have to take into consideration that we can't tell the difference between one eye and the other eye. There are 26 goldfish in the tank at the store. How many ways can Ben choose 5? It's a combination. It doesn't matter which 5 he picks. All 5 are going home with Ben. Okay? Now, you have next up in your lovely packet of papers there something called Homework 1. Homework 1 is a bunch of problems that you need to put together, that you need to complete, and then check. I will pause the video, or I will pause the video. You should pause the video now, and then you can come back and take a look at it. I won't be explaining it. I will simply show it, show the solutions, and you can check your answers. You can pause the video as necessary. Okay, so go ahead and pause the video now, and then come back to it after you've finished Homework 1. It's important that you try it. Anything that you don't understand, please check with me. Okay, before we get to May and you have your test on this, check with me. Thanks. You're back? Great. Okay, here's this first page. Okay. Find the total number of outcomes that are possible. This is just the counting principle. Not factorials, not permutations, not combinations, just the counting principle. Okay? Everybody doing good? All right, again, you can pause the video if you need to take longer. Next up, we're doing some factorials, and then a permutation and a combination. Okay, and then explaining why the answers differ. So again, take a look at this. For all of these, you can use Desmos or the calculator. Now, in class on tests, you must use a calculator. On the SOL, you may use Desmos or the calculator. All right, again, pause the video if you need it. Here, we get to number 16. Woohoo! Got to determine if it represents permutation or combination and then solve. So, without further ado, because we've already explained this in the other one, here are these. 16, oops, through 20. We'll get to 25, 21 through 25 in just a minute. Okay, again, pause the video if you need longer to look at it. Here's, I guess I didn't get through 21. There's 21. Firecracker, remember, it's got multiple letters that are the same, so you simply have to divide by the factorial of those out. We can't tell one R from another R, one E from another E. Okay, 22 through 25. Take a look. Did you crush it? Are you getting it? And again, remember, you don't have to do the formula. You could do the Desmos or calculator version of this. You will need to be able to do the calculator in class on the SOL, calculator, or Desmos. Great. In summary, permutations are arrangements of objects from first to last where order in which the objects are selected is most important. Factorial notation is simply the number followed by an exclamation point. It does not mean to scream the number out loud. It means take that number, multiply it, times every number below it, every natural number below it, down to 1. 0 factorial is 1, because you can arrange 0 objects one way. A permutation, it's Out of how many things do you want to arrange how many things? Order matters. Combinations, order doesn't matter. It just means I'm going to have a group of some number of objects out of some number. If I'm going to take the entire group, there's only one way to have a group of the entire group. All right? Great job.